So I want to talk about how Machizuki's recovers inertia groups. Of inertia groups. Of cusps. And all right, and so I'm just going to start. So here's a lemma. So if R is bigger than or equal to 1, then this group, 2GR, so this is like the fundamental group of a genus G curve with R marked points. It's always isomorphic to a group like this, AI, BI, CJ, where satisfying this relation, I is 1 up to G, we have these commutators. Okay, so this is something we've already talked about. To R of CJ, this is 1. Okay, is isomorphic to F 2G plus R minus 1, the free group on 2G plus R minus 1 generators. Okay, so this is something that we're going to need to use to start to recover the inertia groups of cusps. Okay, so how are these two things related? Well, the idea is we're gonna want to recover whether or not R is 0 or not. Okay, and let me just say this: if also if R is not 0, this is not true. If R is 0, then this thing here is not isomorphic to a free group, some free group. Okay. All right. So here's the proof. So we're going to need a particular presentation. So here we're going to write this group GR as the free group 2G plus R modulo some normal subgroup here. So F 2G plus R, this is going to be this free group generated by A1, B1 to AG, BG, and then we're going to have C1 to CR, and then R is going to be generated by the single relation 1 to G, AI, BI. This product from J is 1 up to R of CJ, and then we take this relation and then we take the minimal normal subgroup containing it. So we just kind of take the conjugates by all this thing, and then we take the thing generated by that. Okay, so this is a presentation of this group, and then if we let, okay, so we have this. If we let A be these guys, A1, B1 to AGBG, C be this the group generated by C1 up to CR minus 1. We're going to omit one of these guys. So essentially what we're going to do is we're going to create an injection here. And then, okay, so we'll let these guys. So if we let these guys, we claim that this map AC, so this is the free group on 2G minus plus R minus 1 generators. So this is this group to this guy GR is an isomorphism. Okay, so how do you prove this? So the proof is quite simple. So first the map is surjective, since we can solve for CR using the relation. Okay, and then what else? So then now we'll show the map is injective. So it remains to show the map is injective. Map is injective. Okay, so suppose so there exists some W in this group. So it's just generated with A's and C's up to R, so it does not contain an R, so it's like a word, a free word in these things, such that W is in R. Okay? So now we can write down what this means. So this means that R, okay, so that means that W looks like a product, a finite product from I is equal to 1 up to n of Wi R0 Wi inverse, where R0 is the single relation. So this is what a general element of R looks like. R0 is, again, this product, so it's 1 to G, this commutator, and then 1 to R of Cj. Okay, so we have this thing, and now okay. So we suppose that there's something in the kernel. Okay, okay, or something that maps to 0, and what it maps to 0, given the presentation, this is what it must be. Okay, so okay, so we consider the map. F from so the free group on 2G plus R to this group here, C to the R. So this group, cyclic group generated by C to the R, given by which maps A1 to AG, B1 to BG, and then C1 to CR minus 1 to 1. Okay, so we can specify a ring homomorphism, or sorry, a group homomorphism by specifying how all these elements are where all these elements are sent, and so we're gonna just send them to the identity. So we're gonna make them the kernel of this map. Okay, well, we have f of w. On one hand, we have f of w is equal to 1 since w is in this group. Okay. On the other hand, we have f of w. So this is f of. We wrote down what a single relation looks like. I is equal to 1 up to n of Wi R0 Wi inverse, right? And so all these. Okay, so what happens to R0? So this is okay. So now we have to write this. So this is product I is equal to 1 up to n of f of Wi. So this guy becomes a single C. So this becomes CR, and then we have f of Wi inverse, like so. All right, so this actually looks like CR. Oh, so each of these WIs map to some power too. So I guess this is the product from is equal to 1 up to n. So this is going to be, sorry. So again, this is cyclic. Okay, so sorry. So these are all, this is a map from here to here. So this is cyclic, right? So it's abelian, so these cancel. Okay. And so now we have that this is just CR to the n. Okay, and then this implies that n is equal to 1. Or sorry, n is equal to 0. And hence, W is the identity. Okay, and this proves injectivity. Okay, so what did we prove? We proved that when we have a positive group, that this is a free group here. And then the other claim that I made was that this is not a free group, and it turns out that so let me just state a fact for the second part, is that you can never have a free group modulo some non-trivial group. So I was being really dumb for the second part. The second part follows from definition, but just from the definition of a free group. So a free group has no relations. This, by definition, has relations. Hence, it's not free. Okay, so I was just being dumb. All right. So moving along, we can prove the following theorem using the proposition. Okay, so this is the Abelian recovery of the number of punctures of a curve. Okay, so the statement is the following. If x over k, so this is the local version. So Nakamura had a version. Well, this relates to what Nakamura did for the recovery of cusps, but now this is a local version. So this is a curve of type GR. Let's say K over QP is a finite extension. Then I'm just going to write down a statement. Okay, I'm going to say that M, or let's say R, is equal to the dimension, QL dimension, of VL bar, let's say VL, the weight minus 2 piece, minus the dimension QL of the weight 0 piece, where VL is defined to be equal to, we take the geometric fundamental group, tensor Z hat, and we go to QL, and let's say VL W is the pure component of weight W. Okay, so this is a statement. The second statement is so this is a theorem. Okay, the second, and this appears in absolute Abelian geometry or of hyperbolic curves. Okay. The second statement is that the expression on the left-hand side or the right-hand side of star is Abelian. Okay, by this I mean that this number completely factors through the absolute or the Galois group or the fundamental group of X. Okay, so let's talk about this. So let's do the proof. So again, we're gonna let X bar be the compactification of X, and then we can consider the sequence. So we'll let VL bar, so this is going to be so this is defined to be equal to the Abelianization tensor over Z hat, tensor over Z hat with I doing? Oh, QL. Okay. So, so we have this in the lit I. So this is going to be the sum. So x and xc, the cusps of zx, like so. Okay, so we have this. Okay, so we're going to take this kind of free group generated by the cusps, where this thing acts diagonally on each of these pieces. So these are a bunch of cyclotones. Let's actually do it allotically. Okay, so then, or let's do QL. Okay, so Nakamura's lemma says the following, that we have an exact sequence is an exact sequence of GK modules. All right. So now we have okay. So now what we're going to do is we're going to use the theory of weights to do this. So here you can see that this thing here. So let's call this IL actually. IL. So the dimension of QL of IL is R. So this is the number of cusps, and so this is what we're after. Okay, so we write this out. Okay, so this was a representation that was pure of weight minus 2 by Nakamura. Okay, and this exact sequence respects weights. Okay, so in particular, we have the following exact sequence for every W. Okay. And so this implies that the dimension. So now what do we have? Okay, so this is the dimension of QL of now it's an exact sequence, so it's the middle one minus 2 minus the dimension VL bar of minus 2. Okay, and so let me see, did I put minus 2? Yeah, I put minus 2 there. Okay, so the Tate module is self-dual with Tate twist, so I guess this gives this. So minus, so this is 0. Okay, and so what the statement here I'm using is the following. It says that, so let me write this down. I have it. So this is really saying that if X is a principally polarized, okay, well, we're going to have that the Tate module, this is, so this guy, sorry, let's do it like this. Let's do it T. So this is the dual abelian variety. Since it's principally polarized, we have an isomorphism here, but then there's a natural isomorphism between this and TL X dual 1. Okay, so in particular, this will imply that so that TLX minus 1 is isomorphic to TLX. Okay, so maybe we can talk more about this part, this equality here. Okay, so that being said, now what? So what's my last part? So now I need to. So is that everything? So what's the statement here? Okay. But this thing is pure of weight 0. So like when we do this with weight 0, this is going to be 0, right? So when W is equal to 0, this is going to be 0, and then we get an isomorphism here. So this is the dimension of QL VL minus 2 minus the dimension of QL L VL 0. Okay. Okay, and so this gives us our expression that we want. Okay. So let's do the proof of the second part. And so to do this, okay. So first, observe that. Well, let's just write it out, and I'll just link. So we've done an Anabelian reconstruction of this. We've done an Anabelian reconstruction of the Frobenius, right? And in particular, this includes the so this thing gives this in particular, once we have that subgroup as these intersection of groups which look like they're coming from base change. This gives us this sequence here, G. G is, and then we just define this to be, pi mod delta. This is pi. This is delta. Okay, and then we from this from the what we call local class field theory on crack, we get the Frobenius here, right, and we get this Frobenius actions. So we get Frobenius plus the representation, or the value representation on each part on delta of x. So we get this outer representation. And once we have that outer representation, okay, given that we know what Q is, so we also can recover Q. So Q is P to the F, okay, where P and F were both recoverable. And and so these were both recoverable, so then it makes sense to talk about the weight decomposition. So makes sense to talk about weight decomposition. Of let's say VL. Okay, so and all those pieces make sense. So this makes this expression makes sense. So this expression here. Right, and that's the proof. So we get to define all those things. Okay, so let's talk about the recovery of inertia groups at cusps in the local case. So here's a lemma. So let x and y, let's let k over qp be a finite extension. Or let's actually, this is quite true in general. So let k be a field. Okay, let f of x over k, or x to y. Let's see. X to y be a morphism of curves. Of type, let's say, g of x, r of x, and g of y, r of y. The map f, let's say, f bar from the compactifications is totally ramified at a single point and unramified elsewhere so if and only if we have the following numerical condition, and it's the following. It says that this thing here looks like to the degree of f, then r of x minus 1 plus 1. Okay, so this is the lemma. So this is just a numerical condition for this, and the proof is really easy. So proof by picture. Okay, so here's x. Let's see, we had x to y. Oh, sorry, let's do this. Okay, so we had x to y. Okay, and so we had some punctures here. So so this number here is ry minus 1. Okay, and so then, so it's unramified at all these points, and this is the degree of x, the degree of the map f, times ry minus 1, and then here is this ramified point, right? We had 1 here, and this is 1. Okay, so this is how you count this.